Divide and conquer algorithms, or recursive algorithms, is one of the first algorithmic tools that many of you may have learned, for example, binary search or merge search. To see the power of divide and conquer, we'll look at a fundamental problem, multiplying two n-bit numbers. Here we'll assume that numbers are huge. For example, they may be thousands of bits long. This will be the case in an application such as RSA. Since they are so large, we can no longer utilize the hardware implementation. We'll see a clever divide and conquer algorithm which is faster than the standard multiplication approach. Another fundamental problem we'll look at is given n numbers, we'd like to find the median element. The numbers are unsorted, so they are in arbitrary order. Can we find the median without first sorting the list? We'll look at a really ingenious divide and conquer algorithm to do just that. Finally, we'll dive into the beautiful FFT algorithm, fast Fourier transform. It's impossible to overstate the importance of this algorithm. It's used in many fields, for example, signal processing. In fact, it was called the most important numerical algorithm of our lifetime. At least that was the case at the time of the quote in 1994. To understand FFT, we're going to have to recall some basics about complex numbers. Once you understand the basic mathematics behind it, you'll appreciate the beauty and simplicity of the algorithm. It'll take some time and mental effort to get up to steam for the FFT algorithm, but it'll be worth it. It's a masterpiece. The next topic we'll dive into is the divide and conquer technique. We've seen a few examples of divide and conquer already. We saw two examples in the RSA algorithm. The first was the fast modular exponentiation algorithm, which used the repeated squaring idea. The second was Euclid's GCD algorithm. These are two fairly simple applications of divide and conquer approach. We're going to see some more sophisticated examples in the following lecture. What we're going to look at now is multiplying n-bit integers. One of the applications of this problem is in the RSA algorithm setting. There we have huge integers. The number of bits is like 1,000 or 2,000, so the basic arithmetic operations like multiplication are no longer built into hardware. The problem formulation is we're given two n-bit integers, x and y, and we want to compute their product, z, which is x times y. And we want to look at the running time as a function of the number of bits. That's the input size. What we discussed in the RSA algorithm lecture was that the running time using a naive algorithm for computing the product of x times y will take n squared time, order n squared time. What we're going to do now is an algorithm which is faster than this order n squared time. We're going to do a more sophisticated scheme. After this multiplication example, we're going to look at some other sophisticated examples, namely median. We're going to see how to compute the median in linear time. And finally, we're also going to look at fast Fourier transform, FFT. These three examples, multiplying n-bit integers, linear time median, and FFT, are all very beautiful algorithms, and I hope you'll learn to appreciate the essence of the algorithm. Now, one important note is I'm assuming that you've seen divide and conquer before. For example, I'm assuming you've seen things like merge sort, the order n log n time algorithm for sorting n integers. And I'm also assuming that you know how to solve recurrences. If you need a refresher on some of these topics, I suggest you look through the textbook. Now let's go ahead and dive into this topic, multiplying n-bit integers. Before we dive into our example of multiplying n-bit integers, let's take a brief digression. We're going to look at a clever idea from Gauss. It's not at all going to be apparent how this is useful for our multiplication example, but it'll turn out to be a very useful idea which will give us an improved algorithm. Here's a setting that we're working in. Multiplication is expensive, so we want to minimize the number of multiplications. Adding and subtracting is relatively cheap, so we're not going to worry about the number of additions and subtractions. So we're willing to add in additional additions and subtractions in order to reduce the number of multiplications. Now, this fact that multiplications are expensive and additions and subtractions are much cheaper is true in most cases. For example, when we're looking at multiplying n-bit integers, multiplying them takes order n squared time, whereas if we're adding or subtracting, it takes order n time. Now, here's the problem of Gauss. We're given two complex numbers. How do I give you a complex number? I have to tell you the real and the imaginary part. So the first number is a plus bi. A is the real part, b is the imaginary part. And the second number is c plus di. C is the real part, d is the imaginary part. And our goal is to compute their product. We want to compute a plus bi times c plus di. Well, in order to get a handle on it, let's start by just expanding this out. So I get a times c. I get bi times di. I squared is -1, so that gives me minus bd. And then I get two terms which are multiplied by I. The first is b times c, and the second is a times d. In order to compute this product, it looks like we need to compute A times C, B times D, B times C, and A times D. Now each of these, A, B, C, and D, are just real numbers. So it looks like we need 4 real number multiplications. We need to compute A times C, B times D, B times C, A times D. If you give me these real number multiplications, then with 1, 2, 3 additions or subtractions, we can combine these products in order to get the product of these two complex numbers. Now our setting is that multiplications are expensive. So we're trying to minimize the number of multiplications, and we're willing to have additional additions or subtractions in order to reduce the number of multiplications. So, can we reduce the number of multiplications? Can we get it down from 4? Is it possible to achieve this product with only 3 multiplications? It turns out we can do it. The key is that we're going to compute this sum, B times C plus A times D. We'll compute the sum without computing the individual terms. So we're not going to compute B times C, and we're not going to compute A times D, but we're going to compute their sum, BC plus AD. So to recap, we have these two complex numbers, A plus BI and C plus DI, and we want to compute their product. Now our goal is to minimize the number of real number multiplications in order to compute the product of these two complex numbers. We just saw that the naive approach has 4 real number multiplications, A times C, B times D, and BC and AD. Now what we want to do is we want to try to achieve just 3 real number multiplications in order to compute this product. What we're going to do now is we're going to try to compute this sum, B times C plus A times D, without computing the individual terms, BC and AD. That's going to leave us with a method for computing the product of these two complex numbers with just 3 real number multiplications needed. How are we going to get this term, BC plus AD? Well, notice it kind of looks like a cross terms. So let's write out the correct expression so that these are the cross terms. In order to achieve this, we need to have B on one side and C on the other side. And we need to have A on one side and D on the other side. So one side has B and A, and the other side has C and D. Expand this out. Notice these two terms, BC plus AD, is exactly what we're trying to compute. What about these other two terms, AC and BD? Hey, notice these are exactly the products that we're computing in order to compute the product of these two complex numbers. Let's look back at this expression. We're trying to compute this sum, BC plus AD. So let's solve it for this term. If we solve it for BC plus AD, then we get that that's equal to A plus B quantity times C plus D quantity minus AC minus BD. Here's the key now. In order to compute this product of these two complex numbers, what are the 3 now real number multiplications that we need? Well, one of them is A times C, just like before. The second one that we need is just like before, is B times D. The third term that we want to obtain is BC plus AD. That's right here. How can we obtain it? Well, let's use this expression. Look, A times C we already know. B times D we already know. What's the third thing we need? We need A plus B times C plus D. This is the third real number multiplication that we need. If we compute these 3 terms, AC, BD, and A plus B times C plus D, then from those we can compute these 3 terms, AC, BD, and BC plus AD. So the punchline is if we compute these 3 real number multiplications, A times C, B times D, and A plus B times C plus D, then by just doing some additions and some subtractions, we can obtain the product of these two complex numbers. It turns out we're going to utilize this idea in order to multiply n-bit integers faster than order n squared time. But before we dive back into that problem, I want to make sure that you appreciate the cleverness of this algorithm. It's really quite amazing. I mean, look at what you're computing here. You're taking A plus B times C plus D. Now, one of the complex numbers that you're inputting is A plus BI. So what are you doing? You're taking the real part and the imaginary part, and you're adding those up. And that gives you a new real number, A plus B. Why would you consider looking at this number A plus B or this number C plus D? Why would you consider taking the real and the imaginary part of the same number and adding those up? Somehow by looking at the real plus the imaginary part for both of these complex numbers and multiplying those together, that gives us a way for computing the product of these two complex numbers faster. or at least using fewer multiplications. Just think about it for a specific example. Let's say you're trying to compute 5 plus 3i times 7 minus 6i. What are you using here? You're using 8 times 1. So why would you think to use 8 and 1 from these numbers in order to compute the product of these two complex numbers? It's really quite clever. Let's get back to our original problem, multiplying n-bit integers, and let's look at the straightforward divide and conquer approach for this problem. The input to the problem are two integers, x and y, which are both n bits long. And for simplicity, we're going to assume that n is a power of 2. This is a common assumption in divide and conquer algorithms. It allows us to get rid of floors and ceilings in our algorithm description and in the analysis of the running time. And our goal is to compute the product, x times y. We want to look at our running times in terms of n. N is the number of bits for these two integers, x and y. It's the space required to represent these two numbers. Now, what's the standard divide and conquer idea? Think about merge sort. What do? You break the input, the n numbers that you're trying to sort, you break them into two halves, the left half and the right half. Then you recursively solve the problem on the two halves. So for merge sort, that means sort the left half and sort the right half. And then you combine the answers together. You merge them together. Now, how do we apply that same idea here for this multiplying these two n-bit integers? How do we break the input into two halves? Well, we can't break it into x separately from y. So what do we do instead? We break x into two halves, the left half of x and the right half of x, and similarly for y. X is an n-bit number. How do we break it into two halves? Well, we look at the first n over 2 bits and the last n over 2 bits. And we take these first n over 2 bits and we call that a new number, xl. That's the left side of x. And we take the last n over 2 bits, and that's another number, xr, corresponding to the right side of x. Similarly for y, we do the same thing. We take the first n over 2 bits and the last n over 2 bits. So we're going to break x into the first n over 2 bits. That's going to be this new number xl. And we're going to break it into the last n over 2 bits. That's going to be this number xr. Similarly for y, we're going to break it into the first n over 2 bits, call that yl, and the last n over 2 bits, call that yr. Let's look at a specific example to see what this partition of x into two halves is going to signify. Let's look at x equal to 182. In binary, this is 10110110. This is 8 bits long, so we're going to break it into the first 4 bits and the last 4 bits. Here's the first 4 bits. That's going to be xl. The last 4 bits are going to be xr. So xl equals 1011 in binary. In decimal, that corresponds to 11. xr is 0110 in binary, which is 6. How does 182 relate to 11 and 6? Well, notice 182 is the same as 11 times 2 to the 4, 16, plus 6. And in general, x satisfies, we take this number xl, and we multiply it by 2 to the n over 2. That corresponds to shifting it n over 2 times. And then we add in xr, which means add in these n over 2 bits. Let's follow through on our recursive approach. So our basic idea was to break the input into two halves. So we partition this n-bit number x into two n over 2 bit numbers. So xl is the first n over 2 bits of x, and xr is the last n over 2 bits of x. Similarly for y, we partition it to yl, the first n over 2 bits, and yr, the last n over 2 bits. Notice we just saw how xl and xr are related to x. In particular, x equals xl times 2 to the n over 2, that corresponds to shifting it n over 2 times, plus xr. Similarly for y equals yl times 2 to the n over 2, plus yr. Now our goal is to compute x times y. Well, we can replace x by this quantity. X is the same as 2 to the n over 2 times xl plus xr. And we can replace y by this quantity, 2 to the n over 2 times yl plus yr. Now let's expand out this expression and see what we get. Multiplying the first terms together, we get 2 to the n times xl times yl. We get two terms which are scaled by 2 to the n over 2. Namely, we get 2 to the n over 2 times xl times yr. And we also get 2 to the n over 2 times yl times xr. Finally, the last term is xr times yr. If you notice now, we have a recursive algorithm for computing x times y. Now recall, x and y are both n-bit numbers, so we're trying to compute the product of these two n-bit numbers. What we can recursively do is compute the product of two n over 2-bit numbers. Well, we have 4 n over 2-bit numbers over here. so we can compute the product of any pair of them. For example, we can recursively compute the product of XL and YL, and XL and YR, XR and YL, and XR and YR. These are four products of n over 2-bit numbers, which we can recursively compute. This gives us a natural recursive algorithm for computing the product of x times y. Let's go ahead and detail that algorithm to make sure everybody follows what we've done so far, and then we can try and improve on that algorithm. Let's go ahead and detail this straightforward divide and conquer algorithm for multiplying x times y. The input to the problem are these two integers, x and y, which are both at most n bits long, and we assume for simplicity that n is a power of 2, so n equals 2 to the k for some non-negative integer k. And the output of our algorithm is this number z, which is equal to the product of x times y. First thing we do is we break x and y into two n over 2-bit numbers. So xl is the number corresponding to the first n over 2 bits of x. xr is the number corresponding to the last n over 2 bits of x. Since n is a power of 2, these always divide evenly, so we don't have to worry about putting any floors or ceilings on either of these two terms. Similarly, we partition y into the first n over 2 bits, call that yl, and the last n over 2 bits of y, that's yr. Now what we can do is we can recursively compute the product of pairs of these n over 2-bit numbers. We have four n over 2-bit numbers. We're going to take particular pairs, recursively compute their product, and combine those together to get this answer z. The first pair of n over 2-bit numbers that we're going to use is xl and yl. We're going to recursively compute their product, and we're going to store that answer in capital A. The second one we're going to use is xr times yr, and we're going to store that answer in capital B. The last two recursive subproblems that we're going to do are xl times yr, store that in C, xr times yl, store that in D. Now we can get the product x times y using these four quantities a, b, c, and d. In particular, z, which is x times y, that's equal to 2 to the n times a, that's a times, that's not an x, plus 2 to the n over 2 times the quantity c plus d, that's these cross terms, xl times yr, and xr times yl, plus b. We got this expression on the last slide. Finally, z is the quantity that we want to return. Z is equal to the product x times y. That completes the pseudocode for this easy divide and conquer algorithm. Let's take a look at the running time of this algorithm now. Let's go ahead and analyze the running time of this algorithm. How long does it take us to partition x into the 2 halves and y into the 2 halves? These steps take us order n time in order to break up x into the first n over 2 bits and the last n over 2 bits, and similarly for y. How long does it take us to recursively compute these four products, a, b, c, and d? These are each pairs of n over 2-bit numbers. So if we use t of n to denote the running time on the worst case for inputs of size n, then each of these takes t of n over 2, and there's 4 of them. So the total time for these 4 recursive subproblems is 4 times t of n over 2. Finally, given the solutions to these 4 recursive subproblems, how long does it take us to compute z? Well, we have 3 additions of order n bit numbers. How long does that take? That takes order n time. We also have to multiply this order n bit number times 2 to the n. How do we do that? Well, it's much faster than a multiplication, which takes order n squared time. This is just a shift n times. In order to multiply by 2 to the n, we just have to shift this number a n times. Similarly, to multiply this number c plus d times 2 to the n over 2, we have to shift it n over 2 times. So it just takes order n time to do this multiplication by a power of 2. So to compute z, it takes us order n time. So the total time is order n plus 4 times t of n over 2. So let's let t of n denote the running time of this algorithm, easy multiply, on an input of size n. And this is for the worst input. So we take the worst input of size n, and t of n is the running time on that worst case input. We just looked at the running time of our pseudocode, and we saw that t of n satisfies the following relation. We have 4 subproblems of size n over 2 each, and we take an additional order n time to combine these solutions together to get the product of x times y. So the running time for an input of size n is at most 4 times t of n over 2 plus order n. Now if you remember how to solve recurrences, or this is a good time to brush up on it, this recurrence might look familiar. And what you might recall is that this recurrence solves to order n squared. So the easy divide and conquer algorithm that we just described takes order n squared time. So the running time of this divide and conquer algorithm is the same as the running time of the straightforward multiplication approach. Can we improve this? Can we do better? The key thing is, can we improve this 4 down to 3? Can we get away with just doing 3 sub-problems? This is where we're going to utilize Gauss's idea that we talked about earlier. This is the key expression from before. X times y is equal to 2 to the n times xl times yl plus 2 to the n over 2 times the quantity xl times yr plus xr times yl. Finally, we add in xr times yr. Now our straightforward divide and conquer approach computes 4 subproblems recursively. It multiplies xl and yl, xl and yr, xr and yl, and finally xr and yr. We have 4 subproblems, and then it takes us order n time to combine their solutions together. This leads to an order n squared time algorithm. What we're trying to achieve now is we're trying to reduce the number of subproblems from 4 to 3. Thinking back on the idea from Gauss that we talked about earlier for multiplying complex numbers, what do we want to do here? We want to compute this sum, xl-yr plus xr-yl, without computing these individual terms. Well, how do we do that? Well, we think of these as cross terms again. And on one side, we're going to have xl and xr. That's one quantity. The other quantity is going to be yl and yr. When we expand this out, we get the following: xl-yl, xr-yr, and finally we get xl times yr and xr times yl. Now our goal is to compute this sum, so let's solve for that. This quantity, xl-yr plus xr-yl, that's equal to this left-hand side, xl plus xr, times yl plus yr, and then we subtract off these two terms, xl-yl minus xr-yr. Now in the algorithm we just had, this term xl-yl, this was the quantity a, which we recursively computed. xr-yr was b, which we recursively computed. So we have this term xl-yl, and we have this term xr-yr. What's the final term that we want to compute? It's this quantity. So we're going to take xl plus xr, and we're going to multiply that by yl plus yr. And we're going to store that answer in C. We're going to recursively compute a, b, and c, and then we can combine them together using this expression to get x times y. In particular, x times y is equal to 2 to the n times a, as before, plus 2 to the n over 2 times this quantity. How do we get this quantity? It's simply c minus a minus b. c minus a minus b. And then finally we add in b, this last term. And this is going to give us a better divide and conquer algorithm, because now we only have 3 subproblems that we have to recursively compute. And then we can combine them together using this expression in order to get the product of x times y. Let's go ahead and detail the pseudocode for this faster multiplication algorithm. Now this is the algorithm from before. This is the order n squared time algorithm, which utilized 4 recursive subproblems. This new algorithm is fairly similar. It just differs at the end. Just this last bit is different. So let's get rid of the last bit of the algorithm. Let's change the name of this algorithm from easy multiply to fast multiply. The basic setup of the algorithm stays the same. The input is 2 n-bit integers, x and y, and the output is the product. We partition the input x into the first n over 2 bits and the last n over 2 bits. That's xl and xr. And we also do similarly for y. We partition it into yl and yr. Now we're going to recursively compute the product of 3 pairs of n over 2-bit numbers. The first pair, as before, is xl times yl. The second pair, as before, is xr times yr. We're going to store those in a and b as before. Now the new term is we're going to compute xl plus xr, and we're going to multiply that by yl plus yr, and we're going to store that in C. This is where we're utilizing Gauss's idea. Now we utilize the expression from the last slide. Z, the product of x times y, is equal to 2 to the n times a, which is xl times yl, plus 2 to the n over 2 times the quantity c minus a minus b. This is where we're utilizing Gauss's idea. Finally, we add in b. Then we return z, which is equal to the product of x and y. This completes our algorithm, and the key fact is that now we have 3 subproblems that we're recursively computing. Now if we look at the running time of our new algorithm, we have 3 subproblems that we're recursively computing. Each is a product of pair of n over 2-bit numbers. And then to combine the solutions from these 3 subproblems, it takes us order n time to get the product of x times y. What does this solve to? Well, let's go ahead and dive into it to give you a little bit of a refresher on solving recurrences. The first step is upper bounding this order n by c times n for some constant c. Now we can substitute in this expression back in for t of n over 2. So we get cn plus 3 times. Now we substitute in for t of n over 2, which gives us c times n over 2 plus 3 times t of n over 2 squared. Collecting terms, we have c times n plus another c times n times 3 halves. Then we have a 3 squared times t of n over 2 squared. Plugging that back in, we get c times n over 2 squared from that term, plus 3 times t of n over 2 cubed. Collecting terms, we have c times n times 1 plus 3 halves plus 3 over 2 squared. The next term is going to be 3 halves cubed, and so on. We're going to get this geometric series. How many terms in this geometric series? What's the last exponent? We're going to keep going until this term is a constant. So there's going to be log base 2n terms. Now we have this geometric series. We got to look at the series, see whether the terms are equal. They're not. Is it decreasing geometric series, in which case the first term dominates? It's not. It's an increasing geometric series because 3 halves is bigger than 1. So the last term dominates. So this whole thing is on the order of the last term. So we get an order n for this term times 3 halves to the log base 2n for this last term. Notice 2 to the log n is the same as n, so those cancel. We're left with 3 to the log base 2n. Let's convert that into a polynomial. You should remind yourself how to convert this into a polynomial. Let me give you a quick reminder. 3 is the same as 2 raised to the power log base 2 of 3. That's the definition of log. So I have this expression 3 raised to the power log base 2n, and I can replace 3 by this expression, and then I raise that whole quantity to the power log base 2n. Now these two exponents multiply together, so I can swap them. So this quantity is the same as 2 raised to the power log base 2n raised to the power log base 2 of 3. Now these two things are the same. Now this is much simpler, because what is 2 raised to the power log base 2n? This is simply n. So now I have n raised to a power, which is a constant, log base 2 of 3. So this recurrence solves to order n raised to the power log base 2 of 3. What is this number log base 2 of 3? Well, if you plug it into a calculator, you'll see that log base 2 of 3 is roughly 1.59. So we went from an order n squared algorithm to an order n to the 1.59 algorithm. And in fact, we can improve this exponent. We can get it arbitrarily close to 1, but there's an expense for that. This constant hidden in the big O notation is going to grow as this exponent decreases. And instead of breaking the input up into 2 halves, we're going to break it up into more parts, and then we're going to have to work harder in order to combine the solutions together. That completes the description and the analysis of our algorithm. But before we move on, I want to look at a particular example to illustrate the cleverness of the approach. So let's take this example. X equals 182 and Y equals 154. If I write 182 in binary, it's 101101110. And 154 in binary is 10011010. Our approach breaks up X into the 2 halves, XL and XR. And similarly, we have YL and YR. XL is 1011, which is 11 in decimal, and XR corresponds to 6. YL corresponds to 9, and YR corresponds to 10. Now what our algorithm does is it first computes XL times YL, which is 11 times 9, which is 99. Then we compute XR times YR, which is 6 times 10, which is 60. Finally, we get the non-trivial weird idea. We take XL plus XR, which is 11 plus 6, and we multiply that by 9 plus 10. That gives us 17 times 19, which equals 323. How from this number 182, which can be broken up into 11 and 6, somehow we're working with 17. We combine these two. Then we get 182 times 154. That equals 99 times 2 to the n. In this case, n equals 8, so 2 to the 8 is 256. Then we take 323 minus 99 minus 60, and we multiply that by 2 to the 4, which is 16. Finally, we add in the last term, 60. And if you plug that into your calculator, that exactly equals 28,028, which is exactly 182 times 154. And the amazing part is this. 17 and this 19. How do we get those? That's a very non-intuitive part. That completes the description of this faster multiplication of n-bit integers. There are similar ideas for multiplying matrices. That's referred to as Strawson's algorithm. You can look in the textbook to learn about Strawson's algorithm. I'm going to skip it because the algebra gets a bit messy for that. Next, we're going to look at linear time median algorithm. That's a very clever divide and conquer approach.